Our next O'Donnell Awardee presentation in the category of science is by Dr. Sarbajit Banerjee. Dr. Banerjee is the Davidson Chair in Science and Professor of Chemistry and Materials Science and Engineering at Texas A&M University. Dr. Banerjee's work focuses on the interplay of atomistic structure and electronic structure. He has developed an impressive set of predictive design rules for identifying viable metastable compounds, established a powerful toolbox of chemical methods for synthesizing new structures, structures that greatly expanded the current fundamental understanding of his field and explored how unusual structural motifs manifested in these compounds can be harnessed to realize new functions. Dr. Banerjee, it's my pleasure.
Thank you, Dr. Goodsell. Thank you so much for that introduction. I am really grateful to TAMEST in the O'Donnell Endowment for this award. Thank you for everybody, all the Aggies. If y'all don't know, we're nail-biting action in Omaha at College World Series. It's the bottom of the eighth, so thanks for still being here in this room. We're playing Notre Dame, and there's a pretty good chance that we're gonna, make it to the next round. So, you're forgiven for, checking your phone. Exploring metastable phase space, that's what I'm going to talk about today. I'm really grateful to the people that have funded this work, and my research group that has been along for this journey, and my wonderful colleagues at A&M Chemistry, several of whom are in this room. I really appreciate you all being here, making the drive. So this research was funded by NASA, NSF, the Welch Foundation. What a wonderful Texas treasure, and just so amazing to have them here in the state and supporting basic science research. So I've had a lifelong love affair with vanadium, the 23andMe, so the element 23, and so the vanadium industry has been incredibly supportive for everything we do. Another a private foundation, Research Corporation for Science Advancement, has also supported this work. And the Canadian Light Source have a joint appointment there, and they've been extremely helpful in doing a lot of the complex measurements that we do in Saskatoon. So in my research, we often ask this question is, how do you design a new material that performs a specific function across decades of length scales, across decades of time scales? And I'm going to talk about how we go about designing materials, how we go about playing with composition and structure in inorganic materials. And our research has resonance across different teams, so, neuromorphic computing, photocatalysis, and energy storage. I'm going to mostly focus on building a hardware set for AI. So we've heard a lot about the promise of AI, but I'll try to convince you that we're only scratching the surface. There's a whole lot that's left to do, and for which we require a whole new palette of materials. And part of this journey involves navigating these energy landscapes and going and breaking the shackles of equilibrium descriptors. And I'm a chemist, so we start with atoms, and we'd like to manipulate atoms in not just the ways that nature would let us, but in all sorts of ways that go beyond the capabilities of nature, that go beyond the capabilities of equilibrium phenomenon, and then to build up from atoms, sort of architecting at the chemical level atoms to form all sorts of different structures and take it through the level of particles and mesoscale architectures to things you can hold in your hand, right? So that's and a lot of this, anytime we start doing this, intersects with all sorts of real world issues like supply chain that we heard about. There's a wonderful talk from our friends at HEB. And so this is pretty important. So, okay, we've got this vast periodic table, and if you haven't, my freshman class uses this every day. And so if you think about this space, it's a vast space, but it's entirely uncharted, right? So if I were to just throw 3 darts at this periodic table, okay, there's a 99% chance, 95% chance I would arrive on a new material. If I were to throw 4 darts, there's a 99% chance I would arrive on a new material. So this is really this incredible space that is completely unmapped. So when we talk about these landscapes, it's really like exploring a new world. Of course, I mean, there's radioactive elements in there, and perhaps some of them are not so interesting, but there's this vast unknown that we're trying to navigate. And so when we say we don't have materials for computing, we don't have materials for solar cells or so on and so forth, well, we haven't looked, right? So there's this vast space that remains completely unexplored. And so some options, you could search crystallographic databases, but just to give you an example, there's a few 100,000 entries there. Again, and you could say, well, we'll use big data. 200,000 entries is not a huge number for big data, right? So it's a pretty limited scope there of what's been examined. So we can modify known materials, we can combine materials together. What my field is particularly interested in, which is solid-state chemistry, is making altogether new compounds, beginning from atoms and building up from atoms, right? And so you could throw darts at the periodic table. My students sometimes think that's how I pick their projects, but and I'll tell you part of the challenge. Okay, why is this so difficult? So many of y'all are interested in organic chemistry or proteins and such. You can go in and add a methyl group, for example, and such, or an octyl group, and you can draw the structure. If I throw 4 darts at the periodic table, I have no idea what that structure looks like. Right, and without knowing what that structure is going to look like, it becomes very hard to understand its function. And part of the challenge comes from the strong coupling between the spin, charge, orbital, lattice, atomic degrees of freedom, which means that these landscapes can be very hard to navigate. And so one of the things we've been trying to do is, okay, if you pick a certain composition, and I'm not going to go over every composition we looked at, but could you change the atomic connectivity and make altogether new compounds that manifest new function and thereby learn these design rules? And this is, again, something that was a crazy idea that the Welch Foundation has supported and has just led to just, really, really interesting technologies, even, I mean, over a decade or more. And so you could think about this as this very rugged energy landscape. So the lowest minimum is the thermodynamic minimum, right? So that's where nature would want us to be. And then these shallow landscapes also exist. And by navigating them, we can unravel new functions. So let me give you an example. So carbon, okay, graphite is its most stable form. But one of the founders of TAMEST, right, Rick Smalley, found out a metastable form, which does amazing things. Under dinosaurs under a lot of pressure didn't form graphite, they formed diamond, right? So metastable doesn't mean unstable. Diamond is forever. So you can take these metastable compounds and they can realize entirely new functions. So how do we start systematically exploring this landscape that exists of these shallow minima? They're not the deepest wells, but nevertheless have intriguing new properties. And I'm going to talk about vanadium oxides as sort of our palette for doing this and the applications in smart materials and photocatalysis and batteries and such. And so one of the things that'll be apparent to you if you picture these landscapes is you can go back and forth between them. So going back and forth between diamond and graphite is kind of hard. You don't want to turn your diamond into graphite. Okay, that's not how it would be. But you could go back and forth between these, and this gives you the ability to do all kinds of switching phenomena. And why this is really important is the idea that we had about a decade ago. So we all know about this massive data tsunami that is headed towards us, right? So about 10% of all energy now is just data, just moving electrons around, right? So about 1% of worldwide energy consumption is just data centers. Okay, so how do you deal with this, right? And so we've got a pretty good way of dealing with massive amounts of information. So one donut in our brain works pretty well, right? So how do you replicate the behavior of neurons and synapses, right? And so how do you design computers that don't just do arithmetic, but are actually fundamentally intelligent, right? So our brain is really good. If I show you a picture of 4 types of dogs, many of y'all will know the breeds that they are, right? A 3-year-old might struggle a bit because they haven't seen a training set, right? So this is why, but our brain is really good at this compared to like try feeding a picture of dogs into Google, and it'll take about 1 million times more energy, and it might think that it's like a little dog is a cat or something like that, right? So there's some things that our brain's really good at. So how do we go how do we start building out hardware that essentially functions like neurons and synapses and can do things like amplification, thresholding, integration, right? And this cannot be done with silicon circuitry. So the age of AI, why has it been so late? It's been so late because of the sheer computational demand for this, right? So we need to be able to do this at very low energies. We need to be able to, and for this, we need things that are essentially function like neurons. And so this is what we've spent a lot of time doing, is could you design materials that, like this, can switch between being insulators and being metals. So they turn on and off, and with very low power demand. And so hopefully, then this is the big project, and I'm very grateful to Texas A&M and TAMEST for buying into this vision and helping us really stand up a world-class research group, along with my colleague Stan Williams, is how do we back out from the function of a brain to electrical components, and then the fundamental materials building block that will enable these components, right? So how do we inverse design this? And so, well, if we look at this class of materials, right, that has most compounds tend to be insulators, or they tend to be metals. So oxides are a great class of compounds. So if you've got dirt outside that you could go outside and pick, that's pretty insulating, doesn't conduct electricity, and you've got some extremely conducting compounds. But this is a very small class of compounds, especially very small before we started, and it's grown a lot larger ever since, that can switch back and forth. And this is an example of this. So this is vanadium dioxide. It's insulating at low temperatures, but then if I apply temperature or voltage, it switches and becomes a metal. So kind of cool. It goes from being like wood to being like copper. And it does so at very close to room temperature. So there's a very small class of materials that have this massive change in properties. And how do we go about controlling this thing? And it all depends on this very fine balance of some of these properties. Okay, and so there's a couple of different mechanisms. It has to do with very subtle atomic rearrangements that induce this transformation, and that will allow this. And so one of the things we've been interested in is designing compounds that undergo this transformation with very little structural distortion. So most of it is a very subtle change in the positions of the atoms launches this massive change in electronic properties and optical properties. And this is an example of what existed before, and we've really populated this whole set of materials. And I'll tell you about a couple of things that we've done. We've taken this vanadium dioxide compound and learned how to really modify the phase transformation. So Louisa Whitaker-Brooks started this work in my group many years ago. She's now a professor at the University of Utah. And it was carried on most recently by Eric Bram, who's now at the Air Force Research Lab. And one of the things, again, we can navigate these landscapes and identify all of these different atomic configurations that have very different properties through intercalating or substituting different ions. And this is an example that we've also had massive resonance. We've taken the transformation temperature of VO2 to 67 degrees Celsius. We've tuned this temperature by doping different atoms down to close to room temperature. And one of the things that, this seems like esoteric condensed matter physics or solid-state chemistry, but we can embed these inside little plastic films that go on windows. And on a hot summer day like today, they transform and they reflect sunlight in the IR part. So these are not like the thermochromic lenses that cloud up, but they reflect only the IR part of the light, and so they essentially cut down on air conditioning costs. Or on a cold day, they transform back, so you can use the sunlight to heat the interiors again. and this is a company called Dimian that my students have started, that, and several students keep joining them on this incredible journey of entrepreneurship and innovation. One really cool thing we've had fun with is doping boron in, and boron's a very small atom, and it actually likes to move inside, and that has given us an atomic clock, because when we heat it up and then we cool it back down to the low temperature phase, it starts this journey towards its equilibrium structure, and by measuring it, we know exactly how much time has passed. So if anyone was looking to answer the philosophical question, what is time? Time is how much the unit taken for a boron atom to move from one side to another. So it's a fundamental physical constant. Okay, and so it's an atomic hourglass that tells time. And it tells time for a period of months, and it's something that we can use.
Does modern technology still need a little inspiration from the human brain? Let's take a look at a cocktail party. The brain has absolutely no trouble identifying, say, the voice of a friend buried in a din of chatter at the party. But even for sophisticated digital computers, recognizing sounds or patterns within big data can be extraordinarily challenging. Scientists at Texas A&M University are now closer to bringing brain-like computing to silicon chips with their new material. Just like brain cells fire pulses of oscillating currents called action potentials, a compound called vanadium dioxide produces pulses of electric currents when heated. But by adding just a touch of boron to vanadium dioxide, researchers have found that these materials can remember how long it took for them to cool down, mimicking how neurons remember the electrical activity at their synapses. In the future, artificial cells made of vanadium dioxide could even be connected together to form brain-inspired computational networks that leverage both brain architecture and problem-solving abilities.
So that's something we're excited about, and so going beyond this relatively simple palette, we're very inspired by this idea that composition is not structural destiny. So what we've been playing around is this Kirigami approach. So we take these MXV205 compounds, and using low temperature chemistry, we can pull out one ion, and then essentially we can put another ion in, and you can essentially start reconfiguring this whole landscape. And this has functions beyond neuromorphic computing and photocatalysis and battery materials and so on and so forth. And I'll give you an example. So we start with this compound, this is what nature gives us. This is a mineral, and it's very diverse and occurs all over. And then what we do is we stuff different ions into it, like lithium, and then we pull the lithium ions out, and we've got a whole different structure. So this is exactly the same compound, V2O5, but the layers are bent instead of being straight, right? And then we can keep playing games. These are all single crystal structures, and so we can keep playing games with this. So we put copper V2O5, we pull copper out, and now we get this tunnel-structured phase of V2O5, which is where we can very precisely place ions back and manipulate function. And again, this is a new compound that we've discovered. All of these are V2O5 that have entirely different structures. So composition is not structural destiny, and that you could really identify for exactly the same composition many different structures and a design space. And so the way I explain it is, to my students is like, this is kind of like playing Jenga. You can pull out half the blocks, and you put in a whole other different color blocks, and really have this vast space that you can play with and realize new function, very carefully positioning electrons and atoms to realize new function. And this is something that's unpublished that we're really excited about. Joe Handy is the student, and he's taken this tunnel structure and selectively placed lithium ions in 4 different sites. And again, this is something where we can get single crystal structures off, and we can image exactly where the sites go. And I'll end with the composition that Joe made. He's an amateur musician, and showing how precisely sodium and lithium are ordered inside these one-dimensional tunnels of V2O5. sodium and lithium ions occupy a very distinctive position. So with that, I'm again just really grateful for all the colleagues across the world who we work with, particularly Baishang Shu's group at TU Darmstadt and Matt Farr's group at Texas A&M and Dave Watson's group at University of Buffalo, and my wonderful group and 27 PhDs so far who just make me super proud for everything they accomplish out in the world, and we're just it's been the greatest privilege of my life to work with these young folks. Thank you.